Welcome to another member seminar. It's a pleasure to have one of our best, Andrew Best, who is going to talk about ergodic Ramsey theory or a new Newtonian dynamics.
So thank you, Artan, for the introduction. First, I'd like to say I've been at BIMSA since 2021. I was not the first foreigner here, but I was maybe in the second group or so of people who arrived. It's been wonderful to be here. I joined as a postdoc, and now I'm an assistant professor here. Some of you may have seen my talks as a postdoc. But in those talks, there's not really any time to give any intellectual context for my research field of ergodic Ramsey theory. So in this talk, I'd like to do that. But first, let's cut to the point straight away. So it's kind of in the title. So my field is ergodic Ramsey theory. And in one sentence, if you know what that is, it's ergodic theory that is informed by Ramsey theory techniques and problems. If you don't know what ergodic theory is or Ramsey theory is, then that description doesn't help you. So you'll have to wait about 10 or 15 minutes, and then we'll get to the actual math portion of the talk where that happens. But first, before we get there, I'd like to take a historical stroll and describe the distant origins of this field in Newtonian dynamics. Hence this somewhat clickbaity title, a new Newtonian dynamics. So before we begin, I'm speaking to a general audience, which includes some physicists. So I'd like to ask in advance for the forgiveness of the physicists for any errors of a historical nature that concern the very beginning of this field. You see, it is developed in, roughly speaking, two stages from its origins in Newtonian dynamics. And as a result, you don't need to understand physics, really, to do ergodic Ramsey theory. At least so far. Okay. Great. So let's start with Newtonian dynamics. On the screen on your left, you have Isaac Newton. In the picture, you always see of him. The reason it's always that picture, and for many famous kings and queens and other philosophers, it's always this picture, and they always kind of look like this, is because they were literally painted by the same person. My second comment is you can tell it's not AI because the fingers are correct. Okay, so here he is. Give him a like, but leave him alone because he's busy writing this textbook, the Principia, shown on the right. This is the first edition of the Principia. It contained actual errors, which was allowed, is still allowed, but is looked down on. It contained errors which he himself fixed and published a second version maybe 30 years after that. So what's in this book? Casually speaking, this book is one of the most important books in science. It's certainly most important for the scientific revolution. You can find all kinds of good things in this book, like estimates of how big the planets are, descriptions of orbits, some calculus, all kinds of fun stuff, even some musings on comets. It's a 3-volume masterpiece. Great. And for our purposes, it attempts to solve the n-body problem, which we'll describe on the next slide. All right, we'll come back to this dynamical system equals system of differential equations thing in just a moment. But first, let's talk about the n-body problem. Right, so the question that has interested people forever, basically, is some form of this problem. You look up at the night sky, you see these celestial objects, you want to describe how they're moving. It's relevant for your crops, it's relevant because you think they're gods. Who cares what time of history it is? You want to describe the motion of the planets. Great. So the n-body problem, phrased sort of in this modern language, could be said this way: given masses, initial positions, and velocities of n objects, such as planets, not small one things like particles, but planets, describe their gravitational forces exerted on each other over time, and as a result, predict how they will move. All right. So in the Principia, Newton formulates a solution, or at least the beginning steps of a solution to the two-body problem, or one and two-body problem. And the main viewpoint, let's go back, and the main viewpoint there that was so influential for 2 centuries afterward was that you can evaluate this problem as a system of differential equations. If you can solve this system, then you can describe the motion of planets. Great. All right, so this problem drove scientists crazy for decades, centuries. And if you look through your catalog of famous mathematicians, you can usually find that they made some contribution to a special case of the n-body problem, usually a special case of the 3-body problem. So we're talking people like Lagrange, Euler, Poincaré, and so on. Okay. But there's one small problem. It's hard. It's hard to solve this thing. So 2 centuries after the publication of the Principia, we have, let's talk about Poincaré. So Poincaré is working in his maybe early 20s, and he's thinking about a special case of the 3-body problem. And hold on a moment. Sorry, I'm getting over a cold. So he's thinking about a special case of the 3-body problem. And what context is he working in? But it's sort of the end of the 19th century. So this means real analysis was beginning to be formalized. We had these wonderful tools of power series, and we can attempt to use them to solve differential equations. But it's not really working for him. And he makes some observations of a rather soft nature. So instead of attempting to solve the system of equations directly, instead you can make qualitative observations about the phase space. Okay, so I'll say more precisely what this means in a moment. And such initial observations, this change in perspective of not focusing on differential equations, but instead focusing writ large on the properties that all solutions must share, we lead gradually to a viewpoint that is later formalized by famous ergodic theorist G.D. Birkhoff, who you may recognize as having one of the named ergodic theorems, the Birkhoff pointwise ergodic theorem. Okay, so some good ideas by Poincaré. Actually, his partial solution to a special case of the 3-body problem contained a major error. That's okay. Birkhoff comes along and sort of formalizes it a little more, and properly speaking, begins the study of ergodic theory. Okay, so that leads us to our first new Newtonian dynamics. So far, I don't think I've done a good job of communicating the nature of the observations made about the phase space, and I'd like to do that now. So let's start to get a little more formal. So generally speaking, a dynamical system is some phase space X and a group of transformations that act on X. Okay, this group of transformations, for simplicity, we will index by the integers. And so what I want you to think of the phase space as is a collection of snapshots of where the planets are and what their velocities are. So a point in phase space is all of this information contained at once, but there's no time information. All right. So then what the transformation does is it takes this snapshot and let's say it advances forward 1 day. So the planets have moved in some way. So you go from one configuration of planets to another one. And so from this perspective, abstractly speaking, if the passage of time is the map, then obviously the group operation, formally speaking, should be composition. Because if it's today, and I wait 1 day and wait 1 day, that's the same, the planets will be in the same place as if I waited 2 days from today. Okay, so that's where that comes from. And, well, I'll add another comment about what Poincaré did now. So planets are not just some formal mathematical objects, they're physical ones. So in particular, you can use considerations like conservation of energy to describe certain configurations or certain evolutions of configurations as impossible. Okay, so providing this kind of general description of what a solution to these equations of motion must look like is the basis of Poincaré's work here.
You want it to be a group necessarily? You don't want it to be a semi-group?
So I don't want it to be a semi-group until 5 minutes from now.
I see. Okay.
Yeah, or maybe 10. Okay. Yes, moving along one orbit. That's right. Yes. And now to move away a little bit from the n-body problem more towards what Birkhoff was doing, this general setup, well, you can impose lots of, this is a math game, right? You can impose lots of assumptions on your phase space, or different assumptions, and see what kind of theory you get. So forgetting about planets, the most simple example is probably the second one. If your phase space is a compact metric space and your transformation is just a continuous map on it, or maybe a homeomorphism, then you get topological dynamics. And if you impose other structures, then you can get all of these other fields. Okay? Smooth dynamics, complex dynamics. But the one I want to focus on today is ergodic theory, which is the result of assuming that your phase space is a probability measure space with a transformation that respects that structure. Great. This should be very familiar as people who live in the shadow of category theory. Okay. This brings us to our second new development in ergodic theory. So to paint the picture, ergodic theory sort of started at the beginning of the 20th century and had time to develop as its own mathematical science separated from the n-body problem. But a nice coincidence happened. So here's a picture of Harry Furstenberg, who is my mathematical grandfather, and Yuval Paris's PhD advisor. And this is a picture from 1992. Okay, there he is. It's not the official portrait from the Renaissance era, but that's okay. He was sitting in a seminar where this fancy new result that you may have heard of, called Semirates theorem, was being expounded. If you don't know what it says, we'll go over it in a moment. And he thought, by the end of this talk, he had realized that actually this combinatorial theorem could be proven dynamically. And this paper, whose title you can see in the first bullet, initiated my field, ergodic Ramsey theory. Okay, ergodic behavior of diagonal measures and a theorem of Semirates on arithmetic progressions. Great. And so, broadly speaking, we're going to get more technical starting from this slide, starting from the next slide onward. But that's the story of how my field gets there. So we start with Newtonian dynamics. It sort of percolates for a while until we can't solve the system of equations directly. Poincaré says, let's give general descriptions instead. And then Furstenberg realizes from this offshoot of ergodic theory that there are problems in combinatorics and Ramsey theory that can be addressed using techniques from ergodic theory. Okay? And two themes in this, so what this means is that a very common theme in my field is that you get static results by interpreting them dynamically. And so this is called Furstenberg correspondence principle, if you ever hear that. Okay? And the second theme that's pretty common is, well, the advantage of recasting combinatorial results in the language of ergodic theory is that then you can bring all of this wonderful centuries worth of intellectual development to bear on the problem. So in particular, this means a lot of structure versus randomness. It gets very technical, so I'm going to try to keep it limited to that. Okay. If you don't know what Semirates theorem is, and if you don't know what Ramsey theory or ergodic theory are specifically, now's the time to listen. There are some details. So Semirates theorem was an open problem for 40 years. It's one of these Erdős problems. Actually, Erdős and Turan were interested in it in the 1930s. And they were looking at simply sets of positive integers. They wanted to know if there was any structure that could be guaranteed in them. They had this feeling that there must be. And what is this guaranteed structure? An arithmetic progression, at least as far as this problem is concerned. So does a large set of integers contain patterns, contain arithmetic progressions? And the answer is yes, but it took a long time. It took 40 years. Okay, so there was some partial progress on this initially by number theoretic methods. This is known as Roth's theorem. And then Semirates actually proved some limited special case before, and then a year later, the general case of an arbitrary length arithmetic progression. Say it again. So the notion of largeness that's being used here is upper density. So you can think of it as at least infinite, but that doesn't say that much. Okay, so upper density is measured as the lim sup of the relative proportion of your elements in the interval 1 to n. So for example, you can think of the odd numbers or multiples of 3. These very clearly have density 1/2 and 1/3. But because it's a lim sup, it always exists. Yeah, so when you say how large does it need to be, the answer is not very large. However, there are still some number theoretically interesting sets that have density 0. For example, the set of perfect squares or other images of polynomials. However, the strength of this theorem does not come from telling us that the odd numbers contain arithmetic progressions, right? They obviously do. 1, 3, 5, 7, just go on, right? The strength comes from the fact that you know almost nothing about the set, and somehow you deduce the existence of these patterns, and indeed of arbitrarily long ones. Okay, so what I've just told you in embryo is the soul of Ramsey theory. I know almost nothing about the thing I'm working with, and I deduce some structure. That's it. Okay? So this is where the Ramsey theory part of ergodic Ramsey theory comes from. Great. So this is the theorem that Furstenberg realized has a dynamical proof. So on the next slide, I'd like to show you the dynamical version of this statement. So there's a lot of words here, but actually we could ignore most of them. So in particular, we have our usual set of assumptions. Usual because in ergodic theory, we're working with measure-preserving transformations, things that are categorically correct on it. And we're working with, well, because it's measure theory, we expect there to be nothing interesting going on sets with measure 0. So we're working with a set A that has positive measure mu A, bigger than 0. And then we have some conclusion. Now, let's not get lost in the details here. I'm first going to reformulate this conclusion in terms of what it would mean for the planets. Okay, so what this is saying is that if I look up at the current configuration of the planets now, and you tell me how many times you want this configuration to roughly happen. Say it happens 3 times. Then what this theorem would say is that you can wait maybe 1 billion years and 2 billion years and 3 billion years, and at each of those times, the planets will all roughly be in the same configuration. Now just replace 1 billion with whatever other number you happen to get. Okay. Yes, it should be true even for chaotic motions. Actually, when the motion is chaotic, such statements are more likely to be true, simply by pure chance. And I won't make you read the math too much, but in words, the key thing that's going on here is if Semiretti's theorem is about looking for arithmetic progressions in sets of integers, then the way you can kind of see how this is reflected in the dynamical formulation, where the arithmetic progression has been promoted to the set of times where some phenomenon has occurred. So a physical configuration becomes a chronological one. And that's good. That means that ergodic theory is all about telling you what's going on for along special times or eventually, or it's very good at telling you chronological information.
So this kind of definition is insensitive with respect to geometry of X.
So X usually has no geometry. The structure, sorry, just had spicy lunch. The only structure we assume on X is a sigma algebra.
So measure preserving means that your measure functions should stay exactly the same. It cannot get dilated. It cannot get anything, right? It
Yes.
Cannot, yeah. It's just, so that's why it doesn't see the geometry.
That's right.
Okay, I see.
Yes, you can think of it that way. From my perspective, in many cases, there is no geometry. But I will show you some examples in a second where there clearly is geometry.
Okay.
Yeah. Okay, great. So I'd like to take you to the second theme of how proofs in ergodic Ramsey theory usually go without getting too technical, and also show you some concrete examples of measure preserving systems, because I didn't give any. Okay, so the first one that you may have seen before is simply a transformation on the 0, 1 interval mod 1. So fix some real number alpha, and then for each point in 0 to 1, just shift it by alpha. Okay, so here I've depicted the orbit of the point 0. So 0 goes to alpha, blah, blah, blah. When it gets to 7 alpha, then you add 1 more alpha and it wraps around. Great. So this is a very simple example. You would see it in a first ergodic theory class. It's very structured. It's not chaotic, because if I take 0 and I shift it a little bit forward, 0 plus epsilon, then the orbit of epsilon almost looks the same as the orbit of 0. Okay, it's very nice. On the opposite extreme, we have a doubling map. So same interval, 0 to 1, but x goes to 2x mod 1. And I did not even attempt to depict any orbits of this because it gets chaotic very quickly. All right. To see an example of this, if I take the point 0 and I multiply by 2 repeatedly, I'm stuck there. It's a fixed point. But if as soon as I have epsilon, 2 epsilon, 4 epsilon, it's just going around the interval like faster and faster. Right? Just that small change made the difference. Okay, so both of these are measure-preserving systems, and the theorems of ergodic theory describe generally the behavior of systems with respect to recurrence problems. And so when you're in the left extreme, where the system is very structured, often you can just verify directly that the conclusion is true. Because the system is so nice, you know enough, you can just do it. And if the system is very random, like the Bernoulli shift on the right, then you sort of, just by pure independence considerations alone, can usually find whatever pattern or long-term behavior of the system you're looking for. And so a lot of the spice of ergodic theory that's unfortunately kind of technical and hard to convey to a general audience is this interplay between structure and randomness and the actual construction of a general system from parts that behave in these two opposite extremes. And one thing that makes it interesting is that for a given problem in ergodic Ramsey theory, it's not that there's one way to oppose structure and randomness for all of them. And it's not like each problem has its own method. There is significant overlap between different kinds of problems. So it's a rich theory. Okay. So I quite like it.
In what sense is this random?
So it's random in the sense that if you take, if I take a set in 0, 1, and I look at the pre-images of that set along along times like this, then the set along with its pre-images.
Superpose, I get it.
Yep.
It gets superposed.
Yep.
That's why I could get any of those.
Yep. Okay. Cool. So hopefully by now, with my time almost up, I've conveyed to you the main essence of ergodic Ramsey theory and where it came from. Okay? And so with my remaining handful of minutes, I would just like to brag a little bit. So first of all, there are some combinatorial facts where there's no combinatorial proof of them. The only proof is by dynamics. So as an example, the most famous example of this is the polynomial Semeredi theorem, proven by my advisor Vitaly Bergelson and his co-author Leibman, which basically says the same thing as the Semeredi theorem, except instead of looking for arithmetic progressions, you look for structures that are determined by arbitrary polynomials. Okay? So there's no genius analog of Semeredi who knows how to prove this in a purely combinatorial way. We only know how to do this dynamically, and every time I give this talk, I have to check to make sure this claim is true. And it's still true. Okay, great. Another point is that is the second bullet. There are usually many configurations, not just one. So Semeredi's proof does not guarantee many configurations, just one. But for example, here, the statement says there exist x and n such that something is found in a set. And when I say many configurations, I mean for many values of x, there will be many, many values of n such that the configuration can be found. So the theorems can be strengthened even more. And all right, so this is the thing I promised. We can work with a semi-group instead of a group if we want to, Arten. Okay, and actually, from the beginning of ergodic theory, the group that indexes the set of transformations could always have been a semi-group or something with some other structure, like an amenable group. So ergodic theory has been developing a long time, and so things are known about this. All right? But what this means is that a lot of these results can simply be investigated in these other settings. So here I've just displayed a handful of my own results that are repeating this theme of finding many configurations in large sets, but now the large sets are not in the integers, but they're in a countable discrete abelian group, or they're in a countable field or something. Okay. Great. And I want to skip this slide and just talk about future directions. Okay, so to summarize, this field is a very dynamic field, pardon the pun, where research is driven by these old problems and new ones. So a typical open problem in ergodic theory is very hard, and some exciting stuff has happened recently where some of them are being solved, particularly some old problems of Erdős are being solved in rapid fire succession in recent years. And in order to do well in ergodic Ramsey theory, typically you need to have some other expertise from some related field, like one of these that are listed here in the bottom one. Okay, so for example, Terry Tao is very strong in ergodic Ramsey theory, no surprise there, because he can tell you a lot about a lot of these fields in the last bullet. Okay, and the last thing I'd like to conclude with is a small fun fact. Because the field takes a lot of its problems from this wellspring of old Erdős combinatorial questions and musings, it leads to a curious fact that many people in the field have extremely low Erdős number. My Erdős number is 2.
Oh.
That should be relatively surprising. But I'm not that unique. Many people in this field have number 2.
Who did you write with?
Vitaly Bergelson.
I see. He wrote with Erdős? He wrote with Erdős.
And he wrote with Erdős, yes.
Nice.
Yes. Anyway, so I'll stop there. Thank you for listening.
All right. That was a fantastic talk. Questions?
Yeah, nice talk. I had just a generic question about one of your first theorem of yours. How nice are those endomorphisms when you say nice?
Oh, I just mean the image of the group has finite index in the group.
And no additional...
No additional assumptions.
In the previous slides, the condition pi 0 equals 0. What's that about?
So it's to avoid a local obstruction problem. So there are trivial counterexamples if you don't assume some condition on the polynomials.
Okay.
Yeah. Thank you for that. It's a detail I wanted to leave out.
More questions? So this theorem of your advisor, but this is not it. The one which had every positive density set, but this is not that one.
This
Yeah,
one?
right, yeah. So is this, I'm wondering, because you're not saying that your set is equal to this. You're saying it contains it. So why is this very difficult to imagine? If I give you a positive density set, you pick a point in that set, and then you pick number of polynomials as many as the dimensions of where your points are embedded in, and you can always move them with polynomials, shift them. As long as you don't get out of the set, you can always contain them. So why is this very non-trivial?
Well, so it seems that you feel intuitively that the result must be true.
Yeah.
If you have another proof of it, I would be happy to see it.
No, but I want to understand. Obviously, my imagination is wrong somewhere. So I want to see what was the main difficulty? You see, you take a metric set, right? And then it's about containing points. So you're basically saying, if I have a positive measure, positive density set, I can always have some sublocus, subchamber of this set, which is given as orbit of some group acting on the set. And now for the group actions, you're picking them to be polynomials or something, elements of some ring or semigroup.
Well, so the patterns that you're looking for are described by any polynomial that you want, right? So there's some universality property here.
Any polynomial can. That's
Yeah.
less,
So
less,
any structure specified by any collection,
any collection of polynomials.
yes, can be found in any set that's big.
I see.
Yeah.
Good. I see. Okay.
Yes,
Yeah.
but actually, when you have some intuition that this should be true for some straightforward reason, yes, that's right. A common theme in this area is that you can guess what the result should look like, but you won't know how to prove it. Sometimes you can prove it.
I see. And so this one is also very, very specific, right? This is about somehow the metric on the set. So this is your result.
Yes. This one is expressing, so I'm going to ignore the technical part, but this one is expressing the fact that on some scale between ergodic and extremely mixing, depending on what your acting group actually is, some of these intermediate technical properties collapse. That's all.
Okay, so one last naive question. So since you're mainly working on a space of probability distributions, so as you apply some kind of a transformation to this thing, this space absolutely curves up somehow, right? Like in optimal transport theory, as if I'm taking for measurable function, take the distance function, if you like. And then this distance function gets dilated, right? So, but this doesn't see any of the dilations.
So you can think of a general measure preserving system as including many dilations and contractions at the same time.
Okay, but then your measure changes, right?
It doesn't by assumption. So that puts some constraints on what the system is actually doing.
I see.
Yeah.
I see. So if I have a stochastic system which is evolving with time, and at each snapshot of time, I'm looking at probability distribution of a bunch of items, points, whatever, variables. Can I use this theorem for it? Because their distances change, right?
So maybe this theorem will not apply because you may not be working with a measure preserving system.
I see.
There may be related theorems that do apply. For example, there's a whole ergodic theory of non-singular transformations, and it sounds like that property would be preserved there.
Okay. Any questions? All right, that was great. Let's thank him again.